Good morning, ladies and gentlemen. Let's begin our dynamics review. Okay, so heads up, test is on Wednesday. Tuesday night, make sure you get sleep.
Yep, don't stay up late cramming. It's too late. Forget about it.
Wednesday, make sure you eat in the morning. Eat first, and get a little bit of caffeine in you. I'm not talking about like a whole bang, but like have something to drink with maybe a little caffeine to get your brain stimulated. And then maybe have a snack if you need to, and make sure you bring calculator, pencil, ruler, highlighter. For my online people, I'm not entirely sure. Ms. Parker, look at your email and make sure you're reading what Ms. Parker's sending you.
Yeah.
Okay, there we go. Inertia is a property of matter.
Bill Nye the Science Guy.
Bill. Okay, you guys have heard this. Newton's first law, inertia is an object's resistance to change in its motion. We don't fully understand how or why it works, but it is.
Yeah.
More mass is more inertia. Mass is how much stuff is in something.
Yep, this is why you will kick the soccer ball but not the bowling ball.
And then it says accelerometer there. Shall we do accelerometer now?
Uh,
Ever so faintly?
Nah.
Okay.
Nah.
Force, a push or a pull on an object.
It's a simple idea.
Yeah. Force is a vector quantity. The units of force are newtons. Hopefully you're just plowing through this. Force is required to overcome inertia.
That's right. If you want something to move or stop moving, you have to apply a force.
Free body diagrams are useful tools for visualizing the forces being exerted on a single object and writing the equations that represent a physical situation.
Yeah, we've got a scale over here on the wall. If you hang this kilogram from it, what are the forces of acting on the kilogram? Well, a free body diagram uses a dot. So we represent the kilogram with a dot, and there's a force of gravity down. And there's a force of the scale up.
Do you want to call it?
Maybe call it force up, yeah.
Okay.
Fop.
Up.
Fop. And
Ooh, they're
right
equal,
now,
sorry.
there's no acceleration. The force up is equal to force down. And I'm going to say that's about 9.8 newtons.
Mm-hmm.
Or 10 newtons, whatever.
Yeah. Yeah, on the AP test, you guys, you guys can use like 10. That, I mean, please do. They
Yeah.
tell you to, okay? All right. So Newton's first law of motion, an object in motion at a constant velocity in a straight line path will stay in motion unless acted on by an outside force. Sweet.
Yep.
An object at rest will remain at rest unless acted on by an outside force.
Yeah.
Sweet. Okay, when forces are balanced, no acceleration occurs. Equilibrium.
Yep. Equilibrium. Good point. Excellent point.
Okay, the dynamic trinity. Okay, so dynamic trinity, we have three things going on here, and they are all equal to each other. They all...
If you have one, you've got the other two.
Yeah, so if you've got constant velocity, you have no acceleration. I mean, that makes sense. And our net force is 0. If you've got no acceleration, our net force is 0. We've got constant velocity. If you've got one, you've got them all.
Yep. It's an important thing to know.
It really is. Newton's third law of motion shows the connection between the properties of an object and what it takes to move it.
Yep.
Third law, Newton's third law. 3 laws. Okay. So Newton's second law shows the relationship between how massive an object is, the size and direction of the net force acting on it, and the resulting motion.
Yep.
And here we are. Okay, we've got force net equals mass times acceleration. And we've got, for force, of course, we have newtons. For mass, it's kilograms, and acceleration, it's meters per second squared.
Yep.
Net force means two things. So it's the vector sum of all the forces. So it'd be the first force plus the second force, and the first force plus the second force.
Yeah, so the net force right here is going to be 0.
Yeah. Or an applied net force causes a mass to accelerate it. So we also can use it. We also need to be able to use this equation: the net force equal to the mass times the acceleration.
Yep.
Where force and acceleration are vectors, and important, direction of the net force is always the same direction as the direction of the acceleration.
Always. Yep.
Always, 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 always. The force of friction is a force that resists motion. There are two kinds. Static friction resists the onset of motion. So static is not moving. How much, does it take to get the thing moving?
Yeah, if you got this right here, it's not moving. I exert a force, and then it starts moving. So static friction is how much friction there is just before it starts moving.
Just before. That's good. What about kinetic or dynamic friction? Sliding friction, resists motion while in motion.
So that's, once it's moving, it's the force of friction.
It's still experiencing friction, right?
Yeah,
So that's
and-
once it's moving. How much friction depends on two things: how tightly the things are being squeezed together, squeezage, and what kinds of surfaces are it's in contact
For
with.
example, grab that kilogram, and if I pull on this just before it moves, that was about 1 Newton, and put the kilogram in.
I'll just write that down.
You put the kilogram in. Now, it takes a little bit more than that.
Whatever it is, right?
Yeah,
Okay. And so
the-
which one is that, Boykin? That's going to be the
normal force.
right, the squeezage. How much we're adding
Squeezage.
more squeeges there.
Yeah.
Squeeges there. Now, if we put a piece of paper under that, that would change the surface it was in contact with.
That's right.
Right.
And yeah, go ahead.
And what do we do with these numbers, right?
Yeah.
The more normal force equals the more friction. There is a direct relationship between these. The force of friction is proportional to the normal force, but this doesn't help us. We need a constant. The properties of the surfaces determine the coefficient of friction.
And that's symbolized by the Greek letter mu.
And here is our equation.
Yeah, that's how you determine it. It's how much friction divided by how much normal force.
Yeah, so this is our squeezage, and then this is our property of the surface right here, and that would get you the force of friction.
And how do you pronounce that?
Mew!
That's right.
Mew!
The sound the kitty makes.
That's what Leonardo Vincent DiCaprio this morning was sounding like when he wants to be loaded. That's my cat. Okay, like, mew, mew, I just want your food. Okay, free body diagram. Frees you from drawing an object. Yes, it does. We represent that by a dot. Okay, a car by a dot, you by a dot, whatever it is. A dot represents the center of the mass of the object. Arrows are drawn representing the magnitude and the direction of all the forces acting. The net force is found with vector addition.
Yep.
What would be an appropriate system for the bubble part?
Well, we had the, here's the accelerometer. And if you push it to one side, the bubble shows the direction of the acceleration.
Yeah, and where is the bubble when it first, right now?
The bubble goes forward because the water has inertia that resists the motion. And with a bubble cart,
Ooh, that was good. Did you catch that?
yeah,
Okay, good. We've got a little bit of tape here, so I'm gonna go back over here. Okay, so what happens here? We push it forward. Okay, and the bubble goes forward. Right? Did it go forward that time?
yeah, I think
Good.
so. I think you
Okay.
got it.
Yeah, it did.
Yeah, the bubble goes forward.
Okay. So what would be the appropriate system for the bubble cart? Well, we've got bubble cart
We got the table.
and we got the table.
Should we include the Earth?
I think so.
I think we have to
Yeah.
because the Earth is the source of
the
gravity,
gravity.
the interaction of gravity between the cart and the Earth.
So we would say cart, table, and ground, earth. Yeah. Okay. So you do. How do you measure the mass of the measure mass on the International Space Station?
Yeah, how do they're doing experiments, they need to measure mass. How do they do that? I remember doing that with a hacksaw blade.
Yeah, with a hacksaw blade, and then also we read a little segment in the book about like that spring scale,
Chair.
the chair with the restoring force. And whatnot. Okay,
Yeah.
so check that out to refresh your memory. Restoring forces can result in oscillating motion. Okay, restore what? The equilibrium position.
Yeah.
Okay. Inertial mass is the property of an object or a system that determines how its motion changes when it interacts with other objects or system.
Yeah, there's two kinds of mass. Inertial mass is the amount of mass that resists the motion. And that's what we were doing with the hacksaw blade and the washers. You put more washers on there, there's more inertia, there's more resistance to change in its motion. So that's inertial mass. There's also gravitational mass, that's the interaction between objects.
The universe is large and complex, as
It
it
is.
is. Science simplifies by examining an isolated system, an isolated part called a system.
Yeah.
Right? We just talked about that with, what is our system of our bubble cart? A system is an object or a collection of objects. Objects are treated as having no internal structure. That
Makes
sense.
things simple.
Okay. They just exist. Okay, so systems have properties determined by the properties and interactions of their constituent atomic and molecular substructures. So before we said when we're thinking about our system, we ignore them as if they have no internal structure, but they do.
But the properties of the system is determined by everything that's going on,
Yeah.
including the stuff inside.
For an isolated or a closed system, conserved quantities are constant. Now, this is an important slide.
Yeah.
We've hit this, I think, on every single lesson so far.
Yeah.
We have certain conserved quantities. Mass is conserved, energy is conserved, charge is conserved, linear and angular momentum are always conserved.
Yep.
Okay. So I guarantee you're going to get some question about what does the angular momentum of the system change? No, it doesn't. Okay. Okay. An open system is one that exchanges any conserved quantity with its surroundings.
Yeah.
We don't really deal with open systems much.
They make things hard to deal with.
We do closed systems. Can you touch something without it touching you? Right? No, right?
No.
Okay. Newton's third law, forces come in pairs. Yes, Miss Moore, we know this. When two objects interact, one force exerts a force on the other. There is a simultaneous force exerted back, equal in magnitude and opposite in direction.
Yep. Yep. If you smack the wall with your fist, you deliver a blow to the wall delivers a blow to you, equal in magnitude, opposite in direction. That's how bones get broken.
Where was Newton's third law at work when you push the bubble cart across the table? Well, I push the bubble cart across the table, right? The bubble cart pushes back on my finger
Yep.
as I push it. Newton asked, why doesn't the moon follow a straight line path through space?
Object in motion, constant velocity, in a straight line path remain in motion unless acted on by an outside force. So why doesn't the moon follow a straight line path?
What force is keeping it in orbit around us? And it is gravity. Okay, so gravity is a force of attraction that acts between every two pieces of matter in the universe.
Yeah, this is a very large statement.
So what does this say about the force of gravity acting on you right now?
That means you're getting pulled in all directions.
Yeah. I mean, there is a force of attraction between me and this lovely planet Earth. Okay. Right here. Okay. There is an attractive force between every particle in you and every particle in the Earth.
Yep.
We just said that. Okay. Okay. The direction of the force is from the center of mass of one object to the center of mass of the other.
Now this doesn't look like much, but this is a very important idea. This is what allowed Newton to formulate his laws of motion, and especially gravity. If you have to assume that all the mass behaves as if it were concentrated at a single point, and that's called the center of mass.
And if you guys remember, we drew the Earth on the middle there, and we demonstrated that we were looking at the center of the Earth.
Yeah, and what happens
we're
if you
talking about
fall
this.
through a hole that's drilled all the way through the Earth? I don't do that, but
Not possible, right? And so we touched on this idea here. And here's our lovely equation.
Newton's law of universal gravitation.
Okay.
Force of gravity depends on two things: how much mass are attracting each other and how far apart their centers of mass are.
And then the relationships between these are inverse.
Yep.
Right? And then we've got that G, our universal gravitational constant of 6.67 times 10 to the negative 11th Newton meter squared kilogram squared.
And that's a very small number because the force of gravity is weak. You have to have tremendously large amounts of mass in order for it to be detectable.
And then we also have our equation here, which is similar but different.
That's how you find the weight. And
Yeah,
I noticed they both have force of gravity on the left and they both have a little m on the right. but the one on the top's got G times ME over R radius of the earth squared, and the other one has G. And if you recall, interesting thing happened when we solved just G equals times ME over the radius of the earth squared, and we got the acceleration due to gravity.
Okay. Tension. So changing gears here.
Yeah.
Force of tension is a force transmitted by a rope, string, chain, cable, etc.
Yeah, I have some strings here, and there's a force of tension that is up here. It happens to go around the pulley and comes here, and the force of tension that's pulling this way is equal to the force of tension pulling that way.
And how come they're equal, Mr. Boykin?
Well,
They're not accelerating, right?
yeah, we'll talk about that here in, I think, the next slide.
Okay, so force of tension is a fine example of Newton's third law. The force exerted by one end is equal to the force exerted by the other.
Yeah.
Oops, wrong way. When all forces are acting on an object are balanced, when all forces acting on an object are balanced, when the net force sums to zero, the forces are said to be at equilibrium.
And that's what we've got right here. We've got a force in this direction and a force in this direction changed by the pulley, and there's no acceleration. Their net force is going to be zero.
Net force is zero, baby. Okay.
Equilibrium.
And when the net force is zero, the acceleration is zero, and velocity is constant, our dynamic equilibrium.
Yeah, velocity can
Trinity,
be constant over there on the masses in the string that's constantly zero, but it could be 1 meter per second or 1,000 meters per second, as long as it's not changing. The acceleration is zero, the net force is zero.
And in analyzing equilibrium, establish a reference system. All forces in each dimension sum to zero. So what do we do with this? Okay, so think about that Atwood machine problem that we did a while ago. I think it was first semester. It was the pulley and the string, and the pulley only changes the direction of the force.
Yeah, so here we've got the pulley and the string, and what it's doing is changing the direction of the force. And if you recall, we found the mass of a stapler using an Atwood machine.
So what are our steps for this? So we want to make a series of diagrams, and you don't want to cut corners on this. Just draw it out, set it up as given with all the forces. So you would just draw what we have here.
Yep.
You know, using our free body diagram or boxes. I think we ended up using boxes when drawing this. Straighten the string out, right, and rotate the forces. So instead of drawing it like this, now we're straightening it out like that. And then we eliminate that string, right? Because the pulley is just changing the direction of the force.
Yeah, why don't you do a real quick diagram on the board here? Because what we've got here is we've got the pulley at the top, and one is 2 Newton. They're both 2 newtons down, and they're in equilibrium. So that's set up as given with all forces. Now straighten the string out.
Okay, did we add the force? Did you have us do that in there?
Not yet.
Not yet. Okay. So now we straighten out the string. Bada boom. Okay. And we still have 2 newtons this way.
2 newtons that way.
Okay, those are the same length.
Yeah, and then
eliminate the string.
yeah. Oh, and by the way, each one of those is 0.2 kilograms. So 0.2 and 0.2, and so 0.2 plus 0.2 is going to be 0.4 newtons total. I beg your pardon, 0.4 kilograms total.
Okay.
And so now we've got equilibrium, but what if one is pulling stronger than the other? Then you could use that to analyze a situation.
Yeah, if that was like 4 newtons or something. And so you could figure out what the net force is.
Yeah.
Right? Okay. Using our equation.
And we spent a considerable amount of time playing with this.
Yeah. Or you could figure out.
Well, and what you've got is your net force is going to be 0, or if you make this 4.
If I make it 4.
4 newtons, then the net force is going to be 2 newtons to the right.
And you can solve for the acceleration.
And you can find out what the acceleration is. So here's an example. The net force is the sum of the 2 forces. You add them together, but it also produces an acceleration on a mass.
And important question: what force is causing the acceleration? What total mass is accelerating?
So when you have a Wimhurst, I beg your pardon, an Atwood machine problem, you have to say what force is causing the acceleration? What's the net force? And that you have to go through all this stuff to get there. And then what is the total mass that's accelerating? You have to add the masses together.
So those two questions help guide you to look at the two net forces at play, and then also the total mass there. That's what those two questions are guiding you towards. Okay. And then any force of gravity balanced by a normal force does not cause acceleration, which we saw with our mass on our scale, right? And then friction, if present, always opposes motion, and we know that.
Yeah.
Okay. So net force.
So if you've got a situation where something like this is happening and there's an acceleration, you've got the force of the pull, you got the force of friction, you got the force of gravity, you got the normal force. It's the interaction between the force of the pull and the force of friction that's making the acceleration, not the force of gravity and the normal force. You got
because these two are canceling each other out, right?
Yes, ma'am.
And so you have to deal with these two right here.
Yep.
Okay, and we got those like vectors, right, for the net force?
Yes, ma'am.
Okay, so, and then this is a really helpful equation. It's what we just talked about. So the net force, the total mass, which was 0.4 here in our example, and then you could solve for acceleration or, whatever. Okay, to find tension in the string, isolate one of the masses. Okay, and use the second law on it. So our net force is equal to force of tension plus the force of friction.
Well, let's just quickly, let's say with this one we've got 2 newtons and 0.4 kilograms. In order to find the acceleration, that'd be 2 divided by 0.4, which is going to be 4 meters per second. I beg your pardon, 2 meters per second?
2 divided by 0.4, and we get 5.
5 meters per second. So the acceleration is 5 meters per second squared. So on our diagram here, you can put acceleration on the third one.
And it would be this
the
way.
acceleration is going to be 5 meters per second. So then, let's say that on the 2 Newton mass on the top there, on the top diagram, this one, it's accelerating at 5 meters per second to the right. 5 meters per second squared to the right. And in order to find the force of tension in the string, what force would produce that acceleration on 0.2 kilograms?
So we want to figure out...
we want to find out the force of tension
right there.
and it's pulling on that mass to produce. And so, first of all, the net force is going to be 0.2 times 5 meters per second, the mass times the acceleration, right? So 0.2 times 5 is going to be
2.5?
2 times 5. I think it's going to be 1.
It is 1.
So the net force is 1 Newton.
Okay.
So net force is 1 Newton to the right. We got 2 newtons to the left.
Sorry, say that again?
So
like that?
The net force.
Oh, that's the force of tension. Excuse me. That's the net force.
The net force is 1.
Let's use this equation right here, right?
Yeah. But here.
So our net force, is going to be our force of tension.
So the net force is 1 Newton.
Yeah, plus 1 Newton.
No, the net force is 1 Newton. We got that from this.
Yeah, 1 Newton right here. Sorry.
Okay, so 1 Newton equals -2 plus what?
-2 plus our question mark, right?
Yep.
This is the force of tension, and this is our
force of gravity on the thing.
on that thing, yeah. Okay.
So -2 plus what is 1 Newton? It's 3.
3, right?
So the force of tension is going to be 3 newtons.
Okay, so let's back up and talk through what we did there.
By the way, let's go ahead and make this 4 newtons as well.
Yeah. Okay, so that's 4 there. And then we'll say this is 4 right here.
Yeah.
Okay. All right, so which means that that's 4 kilograms there. Okay.
So the process we go through is we find out what the 0.4.
Which makes that 0.6. Which makes
Oh, it changes everything. Well, it's the process that matters.
Yeah. Okay, so that's why I was like, gosh, no. Okay, so let's talk through Boykin. Okay, so the first thing we did, if they wanted to know the acceleration of the system,
Yeah.
the first thing that we do is we draw our Atwood machine, and we include our force of gravity down for each, and then we have our masses here.
Yeah.
Then we straighten out the string. Okay, first step. Then we straighten it out,
Yeah.
and we label our forces accordingly. Now this is going this way, and that's going that way.
So the
and string
net
is still
force
there.
between, in this situation for the system, is going to be 2 newtons to the right, because you got 2 newtons to the left, 4 newtons to the right.
Exactly.
But then you get rid of the string.
Yeah, then you get rid of the string, and you guys can see that 4 this way, 2 that way, so net is 2 this way.
Yeah.
So we get rid of the string, and now we add up the masses, which we kind of messed up on because
6
we changed
kilograms,
stuff, but whatever.
0.6.
Okay, and then the next step is, if I wanted to know the acceleration of the system, is we could say, well, we know that the net force is equal to mass times acceleration.
So that'd be 2 divided by 0.6.
Yeah, by
So-
0.6. So 2 divided by 0.6, and I get 3.3.
So 3.3 meters per second squared.
So that means that the whole thing is accelerating 3.3 meters per second that way.
To the right, or yeah, in that direction. So now, then the question is, what's the tension in the string?
Okay, so the next thing that we did was we just isolated one of these.
We isolated
right?
the mass.
I forgot that we had practiced this with them. Okay, so we just chose to look at this one. You could choose the other one as well. So we just look at this, right?
Yep.
And our next goal here was to solve for the net force just on this one. That was our 5th step here.
Yeah.
Okay, so we said the net force,
Well, it'd be 2 times 3.3.
3 times 3.
Or 0.2 times 3.3, which is going to be 0.66.
0.2 times 3.3. It is 0.66. Boy, nice.
So the net force is 0.66.
So we just figured out the net force on we ignore one, and if you wanted to choose this one, you can as well, but we chose this one.
Yeah.
Okay. So then, what did we do next here?
Well, over here on this equation right here, change that 1 newton to 0.66.
Right here.
0.66. And so the net force is 0.66.
So net
Negative 2
force-
plus what is 0.66?
Yeah, and so it's this one plus that one. It's the net force plus this one is going to give us this one right here.
Yeah.
So this one is going to 0.66 plus 2, and we get 2.66.
Yeah.
Okay, so this is now 2.66 newtons. Okay, so this makes sense. Now, the big thing here is just realizing how to use this equation.
That's right.
Right? And we just look at this. Our net force is going to be equal to whatever this is plus whatever that is, and that one's going to be the force of tension.
Yeah. And what we're doing here is reasoning our way through a situation.
Now, you had a question like this on the test for this, so look back at your test work if you still have it. Or look back at the Atwood machine that we did before previously.